So the terms you're going to be looking for to define today, to put into your notes, are family group, valence electrons, alkali metals, alkaline earth metals, transition metals, halogens, noble gases, lanthanide and actinide series, compound, chemical activity or reactivity, chemical stability, and chemical bond. A lot of those we've already talked about. You may already even have a definition in your notes. You saw them in the videos from last week. Family group, valence electrons, alkali metals, alkaline earth metals, transition metals, halogens, noble gases, those are all things we talked about. Compound, we already talked about that. So it's this one, and the last two are the new ones. So look for those in particular when you do your reading. There's 2 assignments we're going to do today. One will be a homework assignment. But the reason I want you to copy this over into your notes is, again, every time you write it down in your own handwriting, you summarize it in your own words, you're going to learn it much more than just reading it on here, okay? I already gave you families of elements, okay? The first one, it covers most of these terms. It won't take you long at all to do the backside. I'm going to give you more than enough time to do the backside as well as read it. So take your time to really read the front side and copy those definitions over. This periodic table is different from the one I gave you, and I just wanted you to see it as an example of how sometimes they organize things differently, how sometimes they color code them differently, I should say, and the numbering might be a little different. You notice they use Roman numerals up here. That's pretty common. You see that in a lot of periodic tables. But you won't find the numbers within the boxes any different. You won't find the placement of the boxes any different. That stays the same. The only time the numbers are different is when they round them off to a different place. You still have an atomic number, you still have an atomic mass. But they may group them a little differently. You can see the color coding that they used here, which is why I have you using just my periodic table. So we have one constant in everything we're doing. I like this periodic table because it does show a lot of information. This is actually a web periodic table. It's a flash animation. And when you click on each of the elements, it tells you about its atomic number, atomic mass, how the electrons are arranged. There's only one shell, and there's 2 electrons in that shell. Tells you the group that it's a member of, all that kind of stuff. Very useful. Now, as we go through these terms today, the first one is family or group. What is family or group? What does that tell you? What is it? Okay, how do you identify a family or group? Zach? By the number of valence electrons. Or put another way, you could say that the family or group are elements with similar chemical properties arranged in vertical columns on the periodic table. Elements with similar chemical properties arranged in vertical columns on the periodic table. This is a family. This particular family is named the noble gases, and this one is halogens, and this one right here, alkali metals. You don't want to include this one, which would normally be right here. That would be what? Hydrogen. What is hydrogen? A nonmetal. That would belong with these over here that are color-coded a little differently. This row here would be the alkaline earth metals. And then the bulk of what's in the middle here is referred to as transition metals, which you can see right there. Okay? You should be able to identify what group something is a member of. You know you're going to see that again. In fact, now that we've had 2 quizzes, you should have a very good idea about what's on the text. Next one, valence electrons. This is something we've spent plenty of time talking about. You should be real comfortable with by now. Valence electrons are located where? Outermost shell. They're like the side that the other atoms get to see. Like I get to see your outer shell. I don't know what's inside. You may have 3 livers for all I know, but I can see from the outer shell. Okay? And that's how these atoms are judged, by their valence electrons. We call it the outer energy level or valence shell of an atom. Members of the same family usually have the same number of these. Usually. There are some exceptions to that. Stable atoms have full valence electron shells, which is often 8 electrons. So if we go back to this periodic table again, remember that we put in helium as one of the noble gases. You can see even this periodic table classified it as a noble gas. Now their color coding is a little different than what we use, but you get the idea. All of these, if I hit neon, look at the number of electrons in the outer shell. 2, 4, 6, 8. It's full. It's stable. We call it chemically stable. When they have 8 in the outside, they're like a king, nobility. They've got everything they need. They don't need anything from anyone else. They don't even react with the little people much because they're noble. They stand alone. And you can see as I click on each of these, you see this? This is just like we did on our protons, neutrons, and electrons sheet, except we had dashes in between. This is the arrangement. 2, 8, 18, 8. Notice all of these have 8 in that outermost shell. They may have a lot more shells and a lot more electrons overall, but in the outer shell, the one that really matters for reactivity, it's 8 every time. Okay? Now, how is it then that helium can be considered a noble gas with only 2? Why is helium non-reactive? Why does that not want to react with other things much?
Because it only has 2 protons and neutrons and electrons.
Okay, in that particular shell, how many can you fit in that first shell? 2. Remember the paper I gave you that gave you step-by-step directions on how to fill the electron shells? It shows you the total, okay, the protons, neutrons, and electron sheet. Did I give that back to you? Yes? I got back most of those. But it shows you can fit 2 in that first shell. After that, you could fit 8, and then 18, and 18, and then the numbers change. Well, 2 is the maximum I can fit in that shell anyway. So if it's already got 2, it's happy. Okay? The reason this one's a noble gas is because its outer shell is full. It's got the maximum it can carry. Once we get over to the rest of these elements, on this row here, period 2, they always have 2 shells. You notice that? Look as I go across. See how the number of shells stays the same? Why? Because it's in period 2. As soon as I get down here to period 3, notice the number of shells. They all have 3 shells. Period 4, they all have 4 shells. If they show the diagram, they don't show it for all of these. Over here, I get some. They have 4 shells. Okay, so you have that to go by. All right. Next, we had alkali metals and alkali earth metals. You took some notes on this last week when we watched videos, and I don't know how much you got down, but alkali metals are very reactive. Soft, silvery, and they're all in family 1. Okay? Soft, silvery, and in family 1. These are all your alkali metals right here. Very reactive. How many valence electrons do all of these have? 1. See? 0.1. 1 on the outer one. Here. 1 on the outer one. Now, let's just consider this. That has 1 electron in its valence shell. What do you think it's going to want to react with? It's going to want to, no, that, well, yeah, the halogens. I'm sorry, I thought you were saying noble gases. It's going to want to react with the halogens because they have how many? 7. And the magic number, of course, is 8. Okay? So, think about this now. One of those atoms, both of the atoms would like to have 8 electrons in their outer shell. You with me? Okay? This one has 1 in its outer shell. Okay? That's what element? Sodium. Now I'm going to come over here to chlorine. And it has how many? 7. And it would like to have 8. Okay. So again, this would like to have 8, and so would this one. Would like to have 8. Well, there's a way to give this one 8, and a way to give this one 8 in its outermost shell, and make them both happy. How do I do it? Well, combine is kind of along the right track. What am I going to do? What's going to happen if I take away one electron from that? How many will it then have in its valence shell? Because remember, the valence shell is the outermost shell with electrons in it. 8. Do you see that? If I take that one away, there's no shell there any longer. There's no electrons. And what does it have in the next shell? 8. You see that? Now if I take that one away and I give it to chlorine, how many does it have in its outermost shell? 8. Everybody wins. You get that? Okay? So if you're over here in group 1, you're going to tend to lose or gain electrons. Lose. It's easier for this one to give, here, I'll give you one of my electrons, and that leaves me with how many in the outer shell now? 8. I know you think 0. Well, remember, that shell's gone. There's nothing in it. So then now the next lowest shell has 8, and everything's happy. Everything's stable. It's easier for it to give one electron than like this one. I could have this, I could do the same thing. I could have this one give away 7 electrons. That would leave it with 8 in the outermost shell, right? Okay? But if I did that, that would take a lot more work to give away 7 electrons than it would to just take one, gain one. So that's why these two love to react with each other, because they have what each other needs. I want to get rid of this one electron. I have just one extra one. If I get rid of it, I'm happy. And I want to gain just one electron, because if I gain that, I'm going to be happy. How many think they understand this? Okay, this is a good preview into the next part of this, chemical activity of elements. So certain elements, like let's say you're in group number 1, you're going to want to gain or lose electrons. Lose. If you're in group number 8, what are you going to want to do? Stay. You're going to want to do nothing because you're already happy. You got everything you need. If you're in group number 7, you're going to want to gain because you only need a few. You only need one electron to make you happy. Now, what do you think is going to happen if you're in, let's say, in the middle here? Let's say like groups 4 and 5. You got 4 or 5 valence electrons. What are you going to want to do?
Gain or lose?
Not gain, not lose, but what's the other possibility?
React.
I could give you $1. You could give me $1, or share. So those are your 3 choices, 3 options of what can happen with the electrons. They can either be transferred to the other atom, and that bonds them together, or they can be shared. One can go one way, they can either lose or gain electron, or they can share them. But if you're in this group, you're going to lose. If you're in this group, you're going to gain. If you've got 4 or 5 electrons, you're going to share. What do you think you're going to do if you have 2 electrons? Gain, lose, or share? Lose. And if you have 6? Gain. Make sense? Do you see the logic in it now, guys? And it has to do with if you add one there, that outer shell is full, and everyone's happy. Everyone wins. Okay, so the alkaline earth metals, they're in group 2. They have 2 valence electrons. They're going to want to combine with what group? 16, because they have 6, and 6 plus 2 equals 8. Okay? Soft to slightly hard elements. And I know as you learn about some of these things, you go, wait a minute, that doesn't make any sense. Sodium, like that's in my salt, is a metal. Remember, a lot of these elements you guys aren't used to thinking of or seeing in its pure form. And you'd be shocked. Some of these elements, if you saw, like, let's say, pure sodium, it's highly reactive, highly dangerous, and that's why it doesn't often exist in its natural form. I shouldn't say its natural form, in its pure form. It's always looking to combine with something else, right? The 1s are looking for the 7s all the time. But some of these metals are so reactive that just exposing them to air would cause them to burst into flames or explode. Some of them are not what you would think of as metals. You might be able to cut them with a butter knife. This soft metal, okay? But that's what they are classified as. Zach?
Then how come like on some food labels it says like sodium, and it gives like a percent? Is that actual sodium? Or is that like
It's not sodium in the pure form, if that's what you're talking about, because it won't stay stable like that. Okay, so we already know which one that's going to react with. Transition metals, elements from families 3 through 12. And as you know, they don't all, like if this is in group 3, that doesn't mean all of those have 3 electrons. If this is in group 4, it doesn't mean they all have 4 electrons. In fact, most of these have 2 valence electrons. You have to look at that exceptions list that I gave you that tells you which ones have how many. These metals are generally less reactive than those in families 1 and 2. Gold isn't as reactive as, let's say, sodium, okay? And they have 1 or 2 electrons. Even though they only have 1 or 2, they still aren't as reactive. There's another thing that accounts for how reactive they are, and you're going to read about that in this one, okay? Halogens, a member of family number 17, are halogens. Sodium chloride, it says they form compounds called salts with metals in family 1. So when 17 and 1 get together, we make what's called a salt. And the most common one, of course, is sodium chloride, table salt. But there are many other salts that you probably wouldn't even think of. But if it's one of those two combined together, it makes it what's called a salt. Noble gases. You already know that they have 8 valence electrons, which means they're stable and aren't going to want to react. Okay, there's a difference between neutral and stable. If I have an equal number of protons and electrons, I have a 0 charge. But that doesn't mean you're not going to react chemically. Okay, the thing that determines whether or not you're going to react chemically is where your electrons are, how many there are in that outer shell. The lanthanide and actinide series, you're going to read about them more. It says, also known as rare earth elements. They are unlike transition elements and are found at the bottom of the periodic table. Actinides such as uranium, number 92, are radioactive. Those with a higher atomic number are not typically found in nature, but are created artificially in the lab by nuclear reactions. So I'm referring to these right here. If we had to insert them up here where they belong, the table would be really wide and short, and it wouldn't fit on a typical piece of paper. It would be impossible to read. So that's why we put it down here, to make it easier to read. These are also much more rare than all these elements, so we don't use them as much. And that's why they're called rare earth elements. And one row is called the lanthanide series, the other one the actinide series. Lanthanide series and actinide series. Everything over number 92 is man-made. A compound, atoms of 2 or more elements chemically combined together, like water. Okay? It's always 2 H's with an O. 2 hydrogens combined together with 1 oxygen to form, when we have enough of it, we have a compound of H2O, also known as water. Chemical activity or reactivity. This is more of what you're going to read about in the second one. Well, we kind of talked about this already. It says atoms combine with other atoms to form compounds. Helium is a noble gas, not reactive, while sodium is in group 1 is highly reactive. Helium, again, it only has 1 shell, and that 1 shell can only hold 2 electrons. The second shell can hold 8, okay? So whether it's the first shell is full or the second shell is full, if our outermost shell is full, we're not going to react. As opposed to all of these that are always missing something in that outer shell. That's when they want to react. Like I said, there's more you're going to read about that determines how reactive something is besides that, but that's one of the main ones. Chemical stability. The most stable arrangement of electrons is when the outer shell has 8, which we already talked about. Atoms will gain or lose or share electrons to achieve this. Just because an atom is neutral, it doesn't mean it is stable. It just means it doesn't have an electric charge. It doesn't mean it's not going to react with other things. And chemical bond occurs when atoms are electrically held together by gaining, losing, or sharing electrons. like you see in table salt. Okay? Once they get together and form sodium chloride, they are bonded because they're gaining, losing, or sharing electrons.